All right, so you've got an epi exam coming up, and I know it can feel like you're trying to memorize a mountain of information. But don't you worry. In the next few minutes, we're going to blast through the absolute must-know concepts that are going to be a total game changer for you.
So, what's the deal? Out of this massive textbook, what do you actually need to know to pass? Well, that's exactly what we're here for. We're cutting through all the noise to focus on the core framework that, let's be honest, examiners absolutely love to test. So, let's get right into it.
Okay, so here's our game plan. First, we're going to start at the top with the best of the best, the clinical trial. Then we'll get into the detective work, how to spot when a study's results might be totally wrong. We'll take a quick look at some different kinds of methods and tools, and then we'll tie it all together with the ultimate exam checklist.
All right, let's dive right in with clinical trials. Now, in the whole world of scientific evidence, these are considered the gold standard. So why is that? What makes them so special? Well, it's because unlike other studies where we're kind of just watching from the sidelines, here the researcher is in the driver's seat, actively testing something. Think about it. Any new drug or vaccine has to go on this epic 4-part journey. It all starts small with phase 1, just a handful of healthy volunteers to make sure it's safe. Then in phase 2, we expand a bit to figure out the right dose. Phase 3 is the big one. We're talking thousands of patients to prove it actually works better than what we already have. And finally, phase 4 is the long game, watching for any rare side effects once it's out in the real world. Okay, exam tip. This little mnemonic is seriously pure gold. You have to remember this sequence. First comes safety, then sizing up the dose, then proving its superiority, and finally, long-term surveillance after the sale. Drill this into your brain. You can pretty much bet you're going to see a question on this. It's actually really simple. A therapeutic trial is for people who are already sick. We're testing a treatment to see if we can cure them. A prevention trial is for healthy people who are at risk. We're testing something to see if we can stop them from getting sick in the first place. It all boils down to who you start with. Are they already sick or are they healthy? Okay, so you've read some headlines, some study that found a cool link between two things. But can you actually trust it? This brings us to a huge concept, validity. And more importantly, the systematic errors or biases that can completely destroy a study's credibility.
And guess what? We've got another killer mnemonic to help you remember these threats. Anytime you're worried a study might be wrong, just think of the word SIC. This stands for the 3 horsemen of bad research.
So what does SIC stand for? S is for selection bias. This means your study group is flawed from the get-go. Like if you only study people who survived a disease, you're missing a massive piece of the puzzle, right? I is for information bias. This is basically garbage in, garbage out. Your measurements are wrong. Think of recall bias, where sick people just remember things differently than healthy people. And C? Well, C is for confounding, and this one is the sneakiest of all. The source material calls this a confusion of effects, which is perfect. Confounding is this sneaky third factor lurking in the shadows that's connected to both the thing you're studying and the outcome. The classic example is coffee and heart disease. It might look like coffee causes heart attacks, but the real culprit could be smoking. Since smokers tend to drink more coffee, it looks like coffee is the bad guy. Smoking is the confounder. It's messing everything up. And that is exactly why confounding is such a nightmare for researchers. It can make up a connection that isn't really there, or it can hide one that is. But the scariest part? It can even flip the results completely on their head, making something that's actually harmful look like it's good for you. And that's incredibly dangerous. Okay, let's switch gears for a second. Epi isn't just about crunching numbers. Sometimes you need to know the story behind the stats, the why and the how. And for that, we turn to qualitative research. So you've got 3 main tools in your qualitative toolbox. If you're dealing with something super personal or sensitive, you do an in-depth, one-on-one interview. If you want to know what a whole group thinks, like about social norms, you get them all together for a focus group. And if you really want to understand a culture or community, you go full anthropologist and just embed yourself in it. That's participant observation. All right, back to the quantitative world. After you've done all the hard work of collecting your data, you have to summarize it. And using the wrong statistical tool here is like trying to hammer in a nail with a screwdriver. It just doesn't work, and you're probably going to make a mess.
Basically, all the data you'll ever see can be sorted into one of 4 buckets. You've got nominal data, categories with no order, like blood types, A, B, and O. Then there's ordinal data, categories with an order, like disease severity, mild, moderate, severe. Then you have discrete data, which is just countable whole numbers. You can't have 2.5 kids, right? And finally, continuous data, which can be any value on a scale, like height or weight.
Okay, listen up. If you remember one thing about stats for your exam, make it this. It is so important. If your data looks nice and clean with no crazy high or low numbers, you use the mean and standard deviation. But the second you have outliers, those numbers will totally throw off your average and make it useless. That's when you bring in the median. The median is the superhero that isn't bothered by outliers. Okay, this is it, the grand finale. We're going to take everything we've talked about, trials, bias, confounding, and put it all together into one ultimate framework. This is the checklist you need to run through every single time you look at a study's results. And listen, the order here is everything. You have to do it in this exact sequence. Step 1, could this result just be random luck? Check the p-value. Step 2, did they pick the wrong people for the study? That's selection bias. Step 3, were their measurements garbage? Information bias. Step 4, is there a sneaky third variable messing things up? That's confounding. And only if you can confidently say no to all of that can you even begin to whisper the word causation.
All right, let's do a super fast high-yield recap. This is the stuff you absolutely have to know. The 3 biases, SIC. Clinical trials, safety, sizing up, superiority, surveillance. The golden rule for stats, no outliers, use the mean. Got outliers? Use the median. And the final framework, the most important thing, you always rule out chance, bias, and confounding before you ever conclude causation. Got it? So I'll leave you with this thought. The next time you're scrolling and see a headline screaming, "Coffee cures X," or "This one food prevents Y," just pause. Run it through this mental checklist we just built. Could it be chance? Is there selection bias? Is there a glaringly obvious confounder? Using this critical lens isn't just the key to passing your exam, it's the key to being a smarter consumer of science every single day. Good luck.